record on this computer. Perfect. Okay, it's working. Thank you.
Good. All right. So now back to share. Okay, cool. You see this now? Are you seeing the slides? Fix the pond?
Yeah.
Okay. All right, super. I have to warn you that the power on my computer, on my laptop is low, and I'm not at my usual place. So if the battery dies, then I'm sorry, we have to stop the lecture, okay?
Sounds good.
We'll try and go as long as we can. There's nothing much I can do here. All right. So here's the problem. I'm going to let you read this a little bit, and I can summarize for you in a couple of minutes. But first, let's all read this. So it all happens in a shrimp farm. And you're told that there are 2n rows and 2n plus 1 columns. Okay. And what else? Each cell, so yeah, think of these as cells. So this is a large farm. You have square cells. And barriers. You see the barriers? These barriers are over here, and you can flip these barriers. Okay. By the way, how many of you read the problem before? You've seen this before, or you saw it on Saturday?
Yeah, I read it on Sunday.
On like Sunday.
Okay, at least 2, 3 of you, right? Okay, cool. Okay, so you can flip these. These are almost like gates, and you can flip them right at that where you see the little circle. So, for instance, at this center here, over here it was horizontal. Over here it becomes vertical. You see that? So this horizontal thing became vertical. This horizontal one here became vertical here. This horizontal one became vertical here, and so on. So you can flip them. Okay? And then you're asked the question, what are you asked?
If we could trace over each of the cells in the map or in the maze.
Well, you want to get from the starting point to the ending point. You're told that the starting point is right there at the top left, and you're told that the end point is bottom left. And you're asked, can you flip the you want to flip the minimum number of these things in order to get from start point to end point while visiting every cell.
Yeah.
Sounds okay?
Oops.
Right, I see chat questions are you guys were discussing something else. Okay, problem B. All right. Okay, let me get back to this. So you want to know how to figure out the minimum number of flips that you need in order to visit every cell in the pond. Now, if it's like they're set up here, I can go from here to here, and I'm going to end up missing things over here. I'm going to end up missing things over here and over here and over here. Is that clear?
Yes.
On the other hand, if I flip as shown here, these dotted lines show you which ones were flipped. So I flipped 1, 2, 3, 4, 5, 6. Then it turns out that I will end up going from the start to the finish point but I'll visit every cell in the pond. So the question is, how many do I have to flip?
It says that you only have to flip 4 though. Like that's the minimum amount.
How did you figure that out?
It says it in the problem.
It says the problem. Okay, yeah, I think perhaps that's the next slide. Let me see. Well, no, not quite. Okay, yeah, oh yeah, right here. So it says that the answer is 4, whereas here we flipped how many? 6. 1, 2, 3, 4, 5, 6. So you want to find that minimum number, and that's what you're supposed to report. That's what your program is supposed to figure out. Okay. Now, it looks like a horrible problem. It looks like really, really difficult. One of the reasons why it's difficult is because at each of these little circles, right, your barrier could either be horizontal or it could be vertical. So you can think of that as 0 or 1. So what you're saying here is for all the possible flips of the barrier, one of these should work and it should give you the minimum number of flips. And you want to figure out which one that is. And since there are lots and lots of these barriers, and since each one has a 0 or 1 possibility, you really have a lot of different combinations to check. And that makes this problem difficult. Everyone okay with this? Did you understand that?
Yes.
Yeah.
Okay. So by the way, did anyone solve this problem?
Yeah, I solved it not during the contest, but a couple days after.
Okay. So you have a solution. Then I'm going to request that you stay out of telling us how to solve the problem yet. I will ask you towards the end. How's that?
Sounds good.
Okay. But still, feel free to answer some of the simpler questions I ask. So there are a lot of possibilities. For every possible position of every possible barrier, you would get a different answer. A different number of barriers would get flipped. And among all those possibilities, you want to know which is the best and which has the smallest number of flips. So that means, theoretically, it seems that you have to try every possible setting for the barriers in order to figure out the answer. And that's what you want to avoid, because that makes it too expensive. Even if there were only n different barriers, you would have 2 to the n different possibilities for either a horizontal or a vertical flip. And therefore, because this has 2n times 2n plus 1 rows and columns, there really are, something like n squared different barriers. Well, that's not quite true. Yeah, roughly there are going to be n squared different barriers. And so there are 2 to the n squared different possibilities. It just makes the problem way too hard if you were to just do a naive kind of search. Does that make sense? All right, I don't get to see your faces, so I don't really know whether you're saying yes or no, whether you're shaking your head or not shaking your head. Let me move forward. Now, what this tells you is what the input looks like and what the output should look like. The input tells you at every possible gate, it tells you whether it's horizontal or vertical. So over here, you have a horizontal gate, a vertical gate, a horizontal gate, 3 vertical, 3 horizontal, and again, a vertical, horizontal, vertical. This turns out to be exactly what you had before. You'll see here that this one was horizontal, this one was vertical, this one was horizontal. Then in the next row, you had 3 vertical barriers. Then you have 3 horizontal barriers, 3 horizontal barriers, and then vertical, horizontal, vertical. So that's exactly what you have here. Only the first row and the last row have a mix of horizontal and vertical. All the others are either all vertical or all horizontal. If this were your input, then it turns out that you're going to need 4 flips in order to get the best answer. And well, you can go and hand check this and convince yourself that 4 is the right answer. And then there's the second problem below. The second problem has only 1 horizontal gate and 1 vertical, one vertical gate. In this case, since the n is equal to 1, it means that there are 2 rows and 3 columns. And it turns out that if it's horizontal, you can easily get from the start to the finish. And so you don't need to flip anything. That's why the answer is 0. If it's vertical, then you have to flip it to horizontal in order to make it happen. And that's why you need at least 1 flip. So there were 3 problems here, and each one of these has an answer of 4, 0, and 1. Was all this clear to you? If you have any questions, this is a good place to stop me and say, hey, I don't understand this.
So like for like the pseudocode, would we have to like well no, that would be enough. Like would we have to like distinguish, like we would read in the array of like the string of characters and then like put them into like an array or something like that? Or I don't know, like how would we read HVH?
Yeah,
Like
but right now you should not be worrying about the inputs. You should be worrying about the algorithm, because the algorithm is way, way harder than reading the input. So forget the input. Think about the problem. Think about how you're going to solve the algorithm, not the input, not the output. Think about what it is that your challenge is. Is that clear? So you want to understand how the input can be modeled, what kind of computation you have to perform on this, and how you're going to find the answer. We'll worry about the input. I will talk to you about that, but that's you at this point we don't even know how we're going to represent the input. So it's the actual reading is going to become irrelevant for you, and soon you will see that that's probably the easiest part of all of this. Okay. So it turns out that the hard part of the problem is figuring out how you're going to represent the input internally in the computer and what kind of computation it needs. Is it a graph problem? Is it a number problem? Is it a sorting problem? Is it a median problem? What is it? We don't even know what it is, because we don't know how to try every possible solution. Well, clearly we don't want to try every possible solution because we just discussed and said that there are too many possibilities. Okay. So that's where our challenge is. So back to our slides. We're going to start with something very simple. So let me set up the stage here. We know that this is our starting point, where you have the blue star, and the green star is our endpoint. And what this tells us, because of the way the problem is set up, there's always going to be a path from the blue star to the green star. Now, do you even believe that? Why would there be a path from the blue star to the green star always? It turns out that this is not so easy to figure out. And the way to think about this is, if you're right at the start point here, then there is a barrier right next to you, which is either horizontal or it's vertical. If it's horizontal, you have only one way to go, and that's horizontally. So you can only go that way. If it's vertical, there's only one way to go, and that's vertically down. So it seems that you will always have a way to go, and you will, and same thing with the end. The same argument will apply, and therefore you cannot end somewhere else. And in fact, these lines here tell you how you get from the start point to the end point. And in a minute, I'll show you why you could never get stuck somewhere else. Okay, and that is going to become important for our understanding. And so it doesn't matter whether you flip something or not. So for instance, over here, if you were to flip this vertical one to a horizontal one, all that'll happen is you'll go straight like this, and you'll still reach the green star. So it doesn't matter how you set up the barriers, you will always get from the start point to the end point. The question is, will you be able to visit every square in the pond? And that answer we know already. There are going to be situations where you will not visit all the squares, like in this case here. So unless you set them up correctly, you're not going to be able to visit all of them. Now, what happens if I were to? So you can see here how in the end you will be able to always find ways to get from the start to the finish. Now let me show you one more slide. Yeah. So if I'm told that there are horizontal grid points, and horizontal grid lines, and there are vertical grid lines, and the barriers are at the intersections of this, but they're not at every one. They're only at alternate ones. And you see these red dots here. The red dots are where the barriers are, and that's where you either flip horizontal or vertical. And they're not there at every point. They're only at every alternate one, okay? Like in this case. So it's here, it's here, it's here, and then in alternate ones, and then in alternate ones, and so on and so forth. So because of the number of grid lines that you have, your grid is always going to look like this. And what you're trying to do is to get from this point to this point, from top left to bottom left. So let's try and understand what happens when we flip one of these barriers. Remember, right at one of these red points, you can flip a barrier either from vertical to horizontal or horizontal to vertical. In this case, let's assume that it was vertical, and let's say we assume that it was horizontal, and you're trying to flip it to be vertical. And the question is, what impact does this have? Well, it turns out that there is something very, very interesting that happens, and let me explain what that happens. So if you focus on one of the squares right next to the barrier, what you'll see is that right next to the barrier, let's call those cells A, B, C, and D, just so that we can talk about them in a simple manner. And what you'll see is that if the barrier is vertical, then A and C are, there's a path that allows you to go from A to C or from C to A. And same thing, it allows you to go from B to D. But it doesn't allow you to go from A to B or from C to D. And then if I were to look at the other the other barrier here, it turns out, and let's call these cells as E and F. It's quite interesting that depending on how the barrier at this junction is, it all depends on where you're going to come from, where you're going to get away from the A. So back to this, it turns out that if the EF barrier were vertical, then I can go from A to F, but I won't be able to go from A to E. So so therefore what happens is now if I flip that horizontal, instead of going from A to F, I will only be able to go from A to E. Now, all of these sound like useful observations, but we have to make some sense out of this, and that's where some of the next steps are going to become important. So what this means is something very, very important. It says that every cell in this pond has only 2 neighbors that you can visit at any given time. And so if you look at A here, A is adjacent to C or E in the if this barrier is horizontal, and A is adjacent to C and F if both of these are vertical. So depending on whether the barriers are horizontal or vertical, for any given cell, you can only visit 2 other cells, and you will always be able to visit 2 other cells, except for the start cell and the end cell. There, things are a little different, and we're going to try and understand what happens to them. Are there any questions about what I just said? Or have I lost you already? Can I get a response from you guys?
Yeah, so basically, what we just proved is that for any cell, no matter if a barrier is horizontal or vertical, it will have at most 2 neighbors at any time.
You will have exactly 2 neighbors.
Exactly 2. Okay.
Okay, except for the start and the end cell.
Yeah. Okay.
Okay, and that's because of the way these barriers are placed. The barriers are never next to each other, right? They're always alternating. And this barrier could be horizontal or vertical, it really doesn't matter. If it's vertical, then we know that A and C are adjacent and B and D are adjacent. If it's horizontal, then A and B are adjacent and C and D are adjacent. But then, depending on how this other barrier is set, A is either adjacent to E or to F, depending on how that is set. So you always only have 2 neighbors for A. So we are focusing on A, and we know that A is only going to be adjacent to 2, one from the lower barrier and one from the barrier up on top. Okay? Are you with me?
Yeah.
Yes.
Okay, cool. So the effect of flipping a switch from horizontal to vertical is to change the neighbors, but you're still going to have 2 neighbors. Okay, so what you see here is that if this if the barrier at this switch is horizontal, then you'll be able to go this way. Otherwise, you'll be able to go this way. So that's all that'll change. By flipping a switch, you will change the set of neighbors that A has. So either you'll go straight up or you'll go horizontally over here, and that's what we're seeing over here. Okay, so one case you'll go from A to E, the other case you'll go from A to F. All right. Now, so who cares? Why is this important? And this is where we're going to look at some further stuff. Now, what I'm going to do is to take the pond, and I'm going to draw all the neighbors for each of the cells. Now, what we know is that for every cell in the pond, there are exactly 2 neighbors, except for the start and the end. And you see that clearly in this picture. The start and the end has only 1 neighboring cell, right? But everything else, like this cell has 2 neighbors, this cell has 2 neighbors, this cell has 2 neighbors, and so on and so forth. So every cell has 2 neighbors, except for the start and the end. Do you believe that now?
Yeah.
Everyone okay with this?
Yeah.
Yeah.
Okay, cool. So what? Now, we know that because every cell has two neighbors, if I were to actually draw the graph that connects these cells, you'll see that it looks something like this. You will have one path that goes from the start to the finish, because we know that the start has to be connected to the finish. But everything else will simply consist of plain cycles. You won't have any other edges. You won't have any other cells neighboring to anything else, because if, let's say I were to look at this particular cell here that I'm showing you, yeah? It has only two neighbors. So it already has these two neighbors. It cannot have a third neighbor. So it cannot branch out and go somewhere else. So all you can get is a simple cycle. Okay. So because every cell is adjacent to only two, we end up with nice cycles and one path. All right. Are you with me so far? Any questions?
So like for this we would use like depth first search, right? And like
Don't go there. Right now,
okay.
we're just trying to understand the problem. I
Okay.
will ask you at one point, and you can tell me that answer.
Okay.
Hold on to your ideas on how to solve it for a few more minutes, okay?
Like
But your thinking is good, so hang in there. So we now understand a bit more about the problem. What we know is that there is a path. There is always a path from the start to the finish, but we might miss some things. And the reason we miss some things is because they form nice little cycles and there is no way for us to cut in. Did you understand that? If you look at this particular cycle here, because everything has degree 2, has two neighbors, I can't cut in. If I cut in, then it would make neighbors, right? So if this particular cell here, over here, it has one neighbor to the top, one neighbor to the right, it cannot have a third neighbor. If you did, then you might be able to cut into this cycle, but you can't. Because it has only two neighbors, it ends up forming a nice cycle. And this is
Hello? Hello?
every graph has a degree of two neighbors.
not every graph. If in a graph, every vertex has two neighbors, exactly two neighbors, what does the graph look like? Yes, Ricardo, you sorry?
A maze?
I'm looking for some other answer. Your answer is not wrong, but it doesn't quite tell me what I'm looking for. Anyone else?
Wait, Professor, I didn't hear the question. What is it?
Okay, let me ask the question again. Let's say you have a graph. You all understand what a graph is, right?
Mm-hmm.
Your vertices and your edges. Now you're told that in the graph, every vertex has exactly two neighbors, exactly two. Okay. Now the question is, what does the graph look like?
Look like a circle.
A cycle, yeah.
Good. So it looks like a cycle, because in a cycle, every vertex has exactly two neighbors. If you had a third neighbor, then you would have things cutting across. Here, you're not allowed to cut across, right? Unfortunately, that's not the complete answer, because why? Why is that not the perfect answer?
Okay, I'm sorry. Can you repeat that again?
Well, somebody just told me that since every vertex has two neighbors, it must form a cycle. I'm saying that's a good answer, but it's not the perfect answer. Why is that?
Because the start and the finish don't form a cycle.
That's right. Because if, let's say, you had two cycles, that also would work out well, because every vertex now has exactly two neighbors, right? In this case, think of a graph that has this cycle and nothing else. Well, this guy has two neighbors, this guy has two neighbors, this guy has two neighbors, everything has two neighbors. But it's not just one cycle, it's actually two cycles. Well, you could also have three cycles. You could also have four cycles. If every vertex in the graph is part of exactly one cycle, then you would have a graph where every vertex has two neighbors and nothing else. Does that make sense?
Yeah.
So what we are told here is that this is actually a graph where every vertex has two neighbors except for the blue star and the green star. So the blue star has only one neighbor. It doesn't have two because it doesn't have anything on this side, right? The green star has the same problem. It has no neighbor on either this side or this side, so it has only one neighbor. Everything else has two neighbors. So this graph here looks like one path and a bunch of cycles. Did you understand that?
Yeah.
So that's the result of all the observations we've made so far. I have power for another 12 minutes or 15 minutes, just letting you know. So finishing the talk earlier, I'm really sorry about that. I could connect on my cell phone, but it's just too much trouble. Are you with me so far?
Yes.
Yeah.
All right. Now, what we're going to do is to understand what happens when we flip an edge. One single barrier. Let's say we flip from horizontal to vertical. We want to know what the heck happens. So this is what we have. We have one path and a bunch of cycles, right? So let's randomly pick one of these barriers. Let's say we pick this guy here. And let's say we flip it from horizontal to vertical. What do you think happens?
We change the neighbors.
We change the neighbors of the things around that barrier. Very good,
Yeah, okay.
right? Now, this is, you see that here, it didn't change this guy here because none of the barriers around it was changed. It didn't change this, it didn't change this. It only changed this. And in this case, it turned out that the path, instead of going from here to here, because the barrier would prevent us from going from here to here, now it allows us to go this way and get back to the green star. Did that make sense? So by flipping a barrier, what did we do?
We added one of the cycles to the start and then end path.
That's right. We took the path and we merged a cycle into it. So as long as we pick a barrier that's on the outside of a circle, of a cycle, then we could, or that's along the border of this path here, then we can get the path to go through that cycle. So essentially, we merged this cycle into the path. That's what happened, right? So by doing one flip, we were able to integrate a cycle into our path. Now, if I were to do this repeatedly, what would happen? If I were to take this guy, this barrier, and flip it, then I would end up integrating that cycle as well into the path. Does that make sense? And I could do the same thing. I could flip this edge, this barrier, and I would end up integrating this particular cycle into the path. So in each case, by flipping one barrier, I can flip, I can integrate a cycle into my path.
Professor,
Yeah.
does the cycles represent the answer? How many cycles there are?
So in the end, that is your answer.
Oh, that makes sense. Because
Right?
we have to. Yeah.
So here you had 4 cycles. That's why your answer was 4. So all I have to do is to flip this guy, this guy, this guy, and this guy, and I'm done.
So it would be the number of components minus 1 because we have to remove the path.
So, well, it's exactly the number of components.
But
oh, you're right. Number of components minus
okay.
1. Number of cycles minus 1. Number of cycles is the answer.
Yeah.
So essentially, it becomes a connected components problem. You want to know in your original graph how many components there were. And you subtract 1, and that's your answer.
So we check if a path is a cyclical or cyclical, and then that would give us part of the answer.
No, it's not cyclical or acyclical. What you do is you start with your original graph. You compute the number of components, connected components. Remember, over here in this picture, the path is not connected to this cycle, right? So you count the number of connected components. There'll be how many components here? There's one cycle here, one cycle here, one cycle here, one cycle here. That's 4. And then this path, that's number 5. So there were 5 components. In the end, you want just one component. So you have to integrate 4 cycles. So therefore, you need 4 flips. That's it. Every cycle will need 1 flip in order to integrate it into the path. So you start with your original graph, count the number of connected components, and subtract 1 from it. That's your answer. Everyone okay with this? So now we're left with trying to figure out, by the way, I have 7% left. So let's see if we can finish understanding this problem. Now we will get to Adriana's question saying, how are we going to read the input? How are we going to figure out what the starting graph is so that then we can apply the connected components? Are you with me so far? Since I have only 5 minutes, could I request you to turn your videos on, if it's not too much trouble for you? At least I'll know whether you're with me or not. Thank you. Thank you, Joshua. All right, cool. So thanks, David. So let's try and understand all the pieces. What we do is we start with our input, construct our graph, compute the number of connected components, and report that -1 as the answer. So the only challenge, you already know exactly how to do connected components. And that Adriana told us, we're just going to run depth first search and compute the number of connected components. The hard part now, after we've understood all of this, is to go from the input to the graph. That's the only challenge left. Everything else is clear. Are you with me? So in order to do that, we have to do a little bit more work. Well, so by the way, this is all explanation as to how we did this. I think I explained all this to you, so I won't really go into the details here. So let's go back to the input and figure out how we're going to go from the input to a graph. And this, it turns out, will require all the things that we discussed a few minutes ago. So the input is over here. Okay, this is our input. From the input, we have to build a graph, and that part is not clear. So what we do is, since n is equal to 3, and we know that there are 2n rows and 2n plus 1 columns, we know exactly where our barriers are going to be. So our barriers are going to be either at I 2j minus 1 or I 2j, depending on whether I is even or odd. That's what it tells you over there. So create your, once you figured out where the barriers are, you create a vertex for each cell. Okay, so you create a vertex for each cell, and depending on how the barriers are right next to that cell, you figure out which one it's going to be connected to. Either it's going to be connected to its horizontal neighbor or its vertical neighbor. Does that make sense? So over here, for instance, you would have, it says horizontal, vertical, horizontal. So if the first barrier is horizontal, that means that the first cell is connected to its horizontal neighbor, but not its vertical neighbor. Since the second barrier is vertical, then you know that the third cell is not connected to the fourth cell on the same row, but on its neighbor along the column, things of that sort. So you apply simple rules and build your graph. And this is the part that I want you to figure out for next Saturday, because that part is somewhat more manageable. So from the barriers, draw your graph, construct your graph. That's your challenge. Okay, once the graph is done, the rest is easy because we just run connected components and we subtract one and we report the answer. Are you okay with this? I am pretty sure my computer will die in about 2 minutes or so. Just warning you. Are we okay with closing shop soon? If you want, I can connect on my cell phone and I can answer questions, but I won't be able to show you slides. Any questions? Ricardo, is it different from what you had done?
No, that's what I did. I didn't do like as good of a proof as you did. I kind of
Okay.
just drew the graph, noticed that when I flipped the barrier in a cycle
Yeah.
and then it connected that. So I
Okay,
skipped
good.
a lot of steps, but got to the same conclusion.
Okay, good. But it's important to understand all the pieces here so that you see the big picture and the small picture. So Ricardo, do you want to give us some advice on how to go from the input to the graph?
This problem was a bit of a pain because it's actually really hard to build the graph for me.
Yeah.
The way I did it is just, I'm not going to give you the straight answer, but I broke it down into test cases. Like there was a case for moving from left to right, a case for moving up to down,
Right.
whether you're in an even column or even row.
Right.
That's a good clue. Start with that.
Yeah.
I
So,
didn't. Oh,
so there is a lot of detail there that I want you guys to figure out, because that part is not difficult. You just have to draw your pictures and convince yourself. But it's possible to do this. Is that reasonable to say, Ricardo?
yes.
Yeah. So do you think you can handle this on the coming Saturday?
We have to draw the graph, right?
You have to go from the input to the graph. Yes.
All right.
So do that by hand first. Take your input, HVH, VVV, HHH, HHH, VHV. Draw your graph by hand, and then you can try to code it up, because you can break it down into different cases, like Ricardo suggested. Okay? So sit down, figure out if your first barrier is horizontal, where is that start node going connected? Is it going to have a horizontal neighbor or a vertical neighbor? Start from there, and then other pieces will start to follow.
Professor,
Yeah.
can you answer questions about breadth first search since we didn't get to that last time?
I could, but I'm not sure my power will last. But yeah, I'm trying. I can try.
Or actually, yeah, you could like share the screen and stuff like with your phone, and maybe you could do the slides from there.
I can't do the slides from there because I haven't mailed it to myself, but I can definitely answer questions.
Okay.
What is your question? What about breadth first search?
Could we use breadth first search to solve the problem too, or is it just
Oh,
stuff?
yeah. So breadth first search can be used for connected components. It works equally well. It's just that every breadth first search will reach all the things that are part of the same connected component. Then you restart the breadth first search, and each time you restart, you're going to get a new connected component. So you could definitely do that here. It's just that I am sold on depth first search. I bet my money on depth first search anytime there's a choice. That's just me. And once you've seen enough problems like I have, you will also believe in depth first search.
Another question.
Other
For connectivity, how would we solve the problem for connectivity?
did I answer your question at the end?
Yes.
Sorry?
For connectivity.
Okay. Yeah. Yeah.
For the connectivity problem for the programming challenge.
Yeah.
What we were the first switch as well.
Yeah.
Okay.
What happened?
Hmm?
You didn't finish your question.
Oh, I'm sorry. For the connectivity problem, are you going to explain to us how to do that one as well?
Oh, you mean the second one? I won't be able to explain that in the three. Remind me the problem. Go ahead and tell me. What was the problem?
It had something.
Summarize the problem for.
It was a connectivity problem. I don't really remember it that well.
Then I'm not sure I could help you right now with.
You're talking about the one where it's railroads and streets?
I think so.
Okay, yeah. So it's the cities and cities, and they're connected via streets and railroads, bidirectional. I think that's what she means.
Yeah, it's the railroad problem where there's N railroads and like you have to like make sure that everything's connected to each other.
No, there's N cities, there's K roads, and L railroads.
Yeah, that problem.
I don't remember the details, David. Can you tell me, remind more?
Let me go to the problem. Connectivity. I'm gonna share both disabled participant screen sharing.
Okay. I can. Yeah. I can
I'll put the link. I'll put the link. I'll put it here.
No, go ahead and open it. Share it.
Oh, okay. Up here. Yeah, it's this problem.
Yeah, this looks more involved. So why don't I prepare something and tell you next time? Yeah.
Yeah, that's fine.
Was anyone able to solve this?
Ricky was.
Okay. Was Ricky, was this easier than the other one?
This one was easier. The other one
But
was more
more-
challenging.
Okay, all right. Yeah, I can prepare something and tell you next time. So yeah, I don't think I can make it this time. Other questions?
No, sir.
Okay.
At least not for me.
All right, guys. I see 1% left on my machine, so I apologize for messing up, but I think we got through the problem, right? You guys figured, you guys understood this, right? I hope. Joshua is smiling, so I guess it must be okay. All right, cool, guys. Shall we sign off? Have a good evening.
Good evening, Dr. Giri.
Thank
Thank you,
Dr. Giri.
Professor.
All right. So next time we'll talk about the next topic. We'll talk about minimum spanning trees.
Awesome. Okay. All right. Thank
Awesome.
you, Professor.
Take care.
Good night.
Thank you.
Bye.
Good night.
Have a good night.